So thank you all for coming today at this session that will concern geometry and medical imaging. The first talk is presented by Adrien Vorer, who is working at the University of Clermont-Auvergne. He will present us his work about diffeomorphic ICP registration for single and multiple point sets. So you have 20 minutes, including the questions, to present your talk.
I know. Thank you.
Thank you, Adrien.
Okay, here we go. So hello everybody, I'm Adrien Vorer from Institut Pascal in Clermont-Ferrand. I'm going to present an algorithm for the registration of point sets with using diffeomorphic registration functions. Wait, oh, wrong. Yeah. I'll start by giving an outline of the method I use to handle diffeomorphisms, which is called the LDDMM framework. It stands for Large Deviation Diffeomorphic Metric Mapping. It's a bit of a funny name, but that's the name that remained like for the last 20 years, so I'll use the name. I'll explain very rapidly the framework for those who don't know it, and then I'll apply it to my own algorithm that I called Diffeomorphic ICP. So diffeomorphism, I guess mostly everybody knows it, but still it's a good introductory slide. So it's in our case, it will be we will work in RD. So it's a bijective differentiable function from RD to itself, whose inverse function is also differentiable. So you see an example here in R2. You can view it as a smooth deformation of a grid, and it should be non-overlapping to preserve the bijective nature of the diffeomorphism. So this is a diffeomorphism, and this is not a diffeomorphism because, wait, how do I point? Yeah, here it's not invertible. Okay, probably you all know that. And you probably, if you're here, most of you know that it's used in medical imaging to basically to compare images together. So for example, you could have a brain image from one monkey and apply a diffeomorphism so that it matches a brain image from another monkey. Basically, you have two structures from, say, different patients, and you apply a diffeomorphism to one of the structures for it to match the other structure. So that's registration. That's what registration means. And you can apply it to brain images, brain structures, etc. So now the mathematical basis of the LDDMM framework for diffeomorphisms. The building block of this framework is that you must have some Hilbert space over your vector field. So in that example in R2, so I have some Hilbert space that I call V. Here's one element of V, so it's a vector field. And whenever I have an element of V, I can define its square norm. In that particular case, that was 5.1. And when I have two vector fields, so two elements in my Hilbert space, I can compute their scalar product. In that case, it was minus 2.6. And there's a technical detail that either you know what it means and then everything, you will understand that part. Either you don't know what it means and I can't explain it in 15 minutes, but it should have a reproducing kernel. It should be a reproducing kernel Hilbert space. So basically, you must have some function k that has that property that basically reproduces the pointwise estimations on your vector fields. And that will come in the technical part, but I won't talk a lot about it. And once you have that, you can define a metric structure over your diffeomorphisms. So start with some abstract space of diffeomorphism. So each point here is a diffeomorphism, and you will build a trajectory smooth from t equals 0 to 1, t equals 0 being the identity mapping. So here I illustrate what happens when I'm in t equals 0.1, t equals 0.2, and you see that your diffeomorphism evolves until it reaches its endpoint at t equals 1. And what you're going to do with that is that you're going to build the speed of this trajectory. So at each time point, the speed will be a vector field. Given by this flow equation here. So basically, V at every time tells me where the point on the grid will be a little further away in time. And it's defined as a flow equation. And so here I'm plotting the trajectory again, but with its speed vector field at every time. And once you have that, Obviously, to make the link with what I showed before, you're going to suppose that every instant in time, your vector field belongs to the Hilbert space that you defined previously. So you can define its square norm, and then you can integrate the square norms of the speeds of your trajectory from the identity to the final diffeomorphism. And you're going to view this as a metric structure over the trajectories in your diffeomorphism space. And the next classic step so that's really the basis of the LDDMM framework. And then the next step will be that you're going to define geodesics in your diffeomorphism space. So a geodesic will be a trajectory achieving a local minimum of this metric cost that I just defined if you impose its endpoint. So you must finish at that diffeomorphism here that I call psi. And if you were to consider another trajectory in your space of diffeomorphisms that arrives at the same point, then the orange one would necessarily have a bigger deviation than the red trajectory. So that's a way to define privileged trajectories in your space of diffeomorphisms, and they are characterized by a classic derivation that you find in most papers about LDDMM. It's basically a Euler-Lagrange variational formulation that characterizes the vector field Vt at every point. So it involves the Lie derivatives of the two vector fields. And you can write it in shorthand, you can write it like that. And you see that it's a differential equation over your vector field Vt. So basically, I'm just talking formally here, but if you know what V0 is, then your whole geodesic is totally determined. And so you know where it's going to arrive. So formally, at least, this determines an equivalence between your initial vector field here, V0, and the final diffeomorphism that you will get following your geodesic. And furthermore, if you look at that equation here, it's easy to show that if you have a geodesic, the norm of Vt square is constant from t equals 0 to 1. So the deviation cost associated to the diffeomorphism psi is just actually only half of the Hilbert norm of the initial vector field. So it's pretty neat, at least formally. If you go into the details, it's not always so clear that it's well defined, but formally it's really clear. Right, so V0 is basically my way of encoding the final diffeomorphism psi, which is here. Okay, so now I will come more to my problem, which is a point set registration, and the ICP my diffeomorphic ICP algorithm is a variation on a well-known algorithm for point set registration, which is called ICP. So I'll start by motivate this by showing the classic ICP functioning, and then I'll just have, when I present my work, I will just have to show the differences, so it will be much faster to explain what I added. So the classic ICP algorithm, it stands for iterative closest point. It was introduced in '92 in the context of computer vision. So you have two sets of points. So this is a structure. The red set and the blue sets the points are not labeled. They don't even need to have the same number of points. They're just like two structures that are described by a group of points. And you want to find, in the original algorithm, you want to find a rigid transformation T that sends the red set to the blue set. And the original algorithm had an empirical way of doing that. They said, let's iterate that at every time we find, for every red point, we find its closest neighbor in the blue set. And then, so that's what we do here. Just find the closest neighbor and then try to update the transform so that each point is set as close as possible to its target. So here's the best rigid transform that I can apply to meet the target. But then when I apply the targets, they have changed. So I must again update the rigid transform. And I do that until it converges. So that was the original proposition. And you see here it's converged. So it's not basically what we would expect. It seems to fall in local minima. So the idea was nice, but it's not very robust. And so rapidly, other variants were developed that I will call probabilistic ICP algorithm. I mean, actually, there's a lot of name. Like it came over and over again during the 2000s. And it's basically always the same idea. You're going to, the first point set, you're going to view it as the centroids of a Gaussian mixture model. So you're going to paste a little Gaussian kernel on each of the points with a given width sigma, which is your single free parameter. It's the isotropic variance around your kernels. And okay, each there's a weight also, but basically generally they're uniform. You put the same weight to all the components. And then once you have a second point set, xn, you're going to formulate your registration problem as a maximum likelihood problem. You want to find the transform t, so the rigid transform in the original versions, and also as a side product, the optimal scaling parameter sigma here that maximizes the likelihood of the warped second set under the distribution based on the around the first set. So, and the nice thing is that this is very well solved with an expectation maximization resolution. So I'm going to show all this in the next slide. So it's still the classic probabilistic ICP algorithm. Your free EM energy, this is the main term. You see that it's basically the square distance between all the warped red points and the blue points, but modulated by these things that are called the responsibilities. It's the EM algorithm that brings these things about. It basically tells the amount of association between each point N and each point C, and you have residual terms that are basically entropies. And so, again, update the targets, update the registration, update the targets, update the registration. What changes before is that since each point is not associated to a single blue point, but to a mixture of them, you know, they can have targets that are smoother here. And so that will create more robustness in your algorithm. And you see that now, as you iterate, you have something that's visually more convincing for a registration of these 2 point sets. Okay, so here's for the literature. Now I can come to what I did, which is diffeomorphic ICP. So I'm going to formulate, so that now that's my work. I'm going to formulate, I'm going to start from a Gaussian mixture model again, but I'll formulate this warped Gaussian mixture model when you add a diffeomorphism. So basically, if this is your distribution, you generate samples, I don't know if you see it clearly, but you would generate samples that are at the basic of those little trajectories here, but then you would apply a diffeomorphism to them. So this is a sample from my warped Gaussian mixture model distribution. And technically, what's interesting is that if you want to define the probability density function of this new distribution, you have the determinant of the Jacobian of the transform that comes into play. And that will be a bit cumbersome because you will have to deal with that Jacobian. And that's the main technical thing that I had to solve compared to what already existed. So now I'm going again to formulate the registration as an inference problem. So I still want to maximize the likelihood, but psi is also there. The optimal diffeomorphism now comes into I also have to estimate it. It also comes into the optimization. And since I want to regularize, I need a prior over the diffeomorphisms that I can use, and that prior will be given directly by the geodesic norm that I explained in the first part. It will be basically the Hilbert norm of the initial vector field that gives rise to the diffeomorphism. And so here it goes again, the EM free energy. So this is the same part as before, but I have two additional terms. I have the log of the Jacobians of my transform at all the data points, and I have the regularization norm over the diffeomorphisms. And I can optimize this thing as before. The E steps and M steps are the same for the responsibilities, for the variance parameter, but for the diffeomorphism, I have to solve it. How do I choose psi to minimize this thing so that I can iterate? I'm not going to go into the detail. I'll just explain basically what I do. So this here is a classic LDDMM registration problem. This is literature. When you have an error function that looks like that and you want to match each point to a target, you know that the optimal vector fields of the geodesics are going to be a finite combination of the kernel at n data points. So you have 2n variables, and you transform your geodesic equation into a 2n dimensional Hamiltonian ODE with some form of Hamiltonian which is given here. All this is like classic LDDMM, so I can't enter the detail. But what happens is that when I have this log Jacobian term that I also need to add to the optimization, first thing is I can rewrite this as the integral from t equals 0 to 1 of the divergence of the vector field. And that's a nicer way to talk about it because it's going to add first order derivatives in the optimization. And so the optimal speed at every point has an additional term, which is the gradient of the reproducing kernel. And the Hamiltonian has additional terms that are based on the gradient and on the Laplacian of the reproducing kernel. So it's just a bit more cumbersome, but basically it's the same machinery as classic LDDMM. And once you have it, so you have your finite dimensional ODE, your free parameter. So what encodes the diffeomorphism is the initial momenta, like basically the initial speed with which you start. That's basically V0. And the whole error function can be rephrased as a function of A0 only, and that's very cumbersome because you have to go through the ODE to compute all these things. So basically you just do brute force gradient descent at this point, and you just optimize over A0 by like an advanced form of trial and error, like gradient descent. Okay, now so this is what it looks like. So you see it's as before, but now the transform is diffeomorphic. You see the little grid that evolves over time, and that sends the red cloud to the blue cloud. It seems to work neatly, but obviously I should do more trials. So the last thing I'm going to talk about is that you can extend this to multiple point set, what's called group-wise point set registration in medical imaging. So you don't have one point set, you have a lot of them. They all were generated with the same GMM, but different diffeomorphisms. And you have all of them, and then you forget about the generating model, and you ask, can I build diffeomorphisms and a common GMM model that will recover the common shape of all these things? So you see that it has to do with building a mean patient in medical imaging and that sort of things. So I'm going to build a diffeomorphism for each point set and a joint GMM model, and I have to learn everything. I have to learn the centroids, the weights, and the sigma. Everything is optimized. So here it goes, and it's again in two steps. So you have your unwarped data point. You do a classic EM model for Gaussian mixtures, so you fit your Gaussian model to the current points, and then you update the diffeomorphisms, then you update the GMM model again, and you do this, and again you see that you're going to converge. You find nice diffeomorphisms that bring all the points to a common underlying shape, and you see that if you remember the shape that I started with, the underlying shape will basically have that sort of C shape that I started with when I generated the points. So it sort of works. Okay, so rapid discussion, summary of what I did. It's a diffeomorphic registration algorithm for point sets. It has the same overall structure as the classic probabilistic ICP algorithm, except the diffeomorphisms are, well, the registrations are diffeomorphic and in the LDDMM framework. And you can extend this to group-wise point set registration, so to build atlases of point sets, say, across patients. There's an existing method to do that, which is actually 20 years old, which when you view point sets as distribution, it's a specific case of, it's a particular case of currents. It's that paper by Glones et al. So we have common elements and different elements. So I'm just going to browse through them very rapidly. The scale sigma is not handled in the same way. The optimization is not exactly the same because I have an EM part. It's not all brute force. Asymmetric match between the structures are not handled in the same way. They can occur in my case. That's a particularity of the ICP algorithm. And you can do group-wise registration in both cases, but here it's with the forward scheme, if you know what that means, whereas here it would rather be a backward scheme in my algorithm. Right, and so to conclude, that was a bridge between two important frameworks in medical imaging, so LDDMM for diffeomorphisms and ICP point set registration. There's some future work here. Apply it to my brain data. Actually, this is already done, but I'm not showing it. And maybe generalize to other structures that can be like surfaces and curves using currents and varifolds. Probably what I showed can also be generalized to these things as it was done for classic LDDMM. And thank you for your attention. This is where you can find the code in Python if you're interested. It's kind of documented. And thank you if you have questions.
So thank you very much for this very clear talk. Are there some questions? I think we have 5 minutes.
First of all, thank you so much for your talk. I guess I have a question about the structure of like optimal solutions, or maybe about the structure of the prior over diffeomorphisms.
Yes.
Like in certain cases, I imagine you're on a space where some sort of global rigid action may register most of the way, and then you can apply diffeomorphisms from that registered
That's
point.
what I do in practice. I first do a rigid registration with some scaling, because you can use the same method, like all the framework is the same, you just use rigid transforms instead of your psi, so basically known stuff. And from there, I applied the so when you see a big shift like I showed, that's not what I do for real. I first apply a rigid transform, and when it's aligned as best as I can, I just showed it like that for clarity. But
gotcha. Yeah, no, thank you. And I guess is there a way to incorporate that into the prior so that that's part of the algorithm? Like
so you could, but I don't know if it's useful. But you instead of using a Hilbert norm here, you could have a semi-norm that allows for vector fields that produce rigid transforms. So the log of a rotation would be a vector field based on asymmetric matrices. And you could say that any asymmetric transform, like a full vector field that produces a rotation, you give it a zero norm and you just put it directly inside the algorithm. Right. So I haven't tested that because I don't know if it's going to bring anything compared to the ugly version of doing in 2 steps. But yeah, that would be nicer in terms of formulation. I thought about it. Haven't tried it though.
Cool. Yeah, thank you.
Yeah.
Hi, thank you for the presentation. I have a short question. It's a diffeomorphic algorithm, so you're handling with diffeomorphisms. I'm wondering, diffeomorphism, it's a global property, and but you mainly use just local properties, like the determinant of the Jacobian is not vanishing. So at which point do you really require that it should be a global property? So at every point, it's a very strong property.
It's the way the LDDMM framework is built. So wait, where would that be? Sorry. When you build a trajectory in the space of diffeomorphisms, if you already have a diffeomorphism and you add a little deviation to it based on a red vector field, if the vector field is small enough, you're going to remain diffeomorphic because you have the identity plus a small stuff, so it remains invertible and whatever you want. And what the LDDMM framework does is just stacks these things. Like you add a small vector field, and then you add another small vector field, but at every point you update the mapping before. You just compose those small transforms, and since every small transform is diffeomorphic, the overall composition will naturally be diffeomorphic.
Okay.
So it's in the, you don't have to worry about it. It will always be diffeomorphic. Just implement that thing, and the way it's built, it can only build diffeomorphism.
Thank you.
Thank you for the nice talk. So your method, you first kind of try to see which points should be matched to which points, and afterwards you kind of try to find the diffeomorphism that achieves that,
yes,
right?
Yes.
So why?
Repeatedly.
Yeah. So why do you need then the diffeomorphism if you already matched it kind of in the first part?
Because you want to transform the whole space. You don't want just to associate points between them. You really want to find a transformation of space that brings the points together. So you're looking for so that would be maybe here. Is that working? Yeah. See, like in this. No, you don't see that. In this toy example here. Those would be 2 brain structures, and you really want to transform the whole brain to match the other one. So if you think of that, you could add some landmarks here, say like this sulcus is here, this sulcus is there, and blah, 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 and I want those points and the whole image behind it to reach some target, and you're interested in what happens to everybody. So if I want to talk about my own data, it's deep brain stimulation. So I have different patients, their brains have different shapes, and when I stimulate electrically here, I know that it improves the state of the patient. But I want to understand like how that would change to another patient. Like if it's some patient that I haven't operated yet, where should I stimulate them? And then I should take what I know from previous patients, but warp it to the new patient so that I have good targets in the new space. So it's a global thing.
So basically you have like a limited amount of points, and you want to kind of infer for the other points which you don't have access to yet to kind of what happens.
Yeah, that's the global idea.
Yeah, okay, sure. Okay, that makes perfect sense.
Other data that you would have.
Yeah, okay, great. That makes perfect sense. Thank you very much. Again, thank you for a nice presentation.
Thank you.
Some other questions?
Thank you for presentation. I was wondering, I couldn't quite grasp the motivation of LDDMM. So is it just to improve the registration performance, or because do you keep the metric structure of LDDMM?
So do you know about LDDMM?
Yep.
So I use the metric structure as a prior. So it comes in the equations, like when I, okay, sorry, that's the problem of the animations. Yeah, here goes. Okay, like here, you see that in my EMM free energy, I have the LDDMM free energy. That's the LDDMM deformation energy here.
Yeah, but what I mean is, does your energy still be define a distance between your images when you do the radiation? Because the main point of LDMM is to define distances. So when you have just the vector field, it will define a distance is a group of diffeomorphism. But when you add the log det,
yes.
Do you keep the metric structure? Because I was wondering if it was the main point was to try to improve the.
No, the log det kicks in. I need it. If I don't have the log det, so there are two parts to the question. But if I don't have the log det, the algorithms don't work. I can show you some slides of that. But the other thing is that wait, where are we? Yeah. Once you boil everything down, you see that my whole energy has this thing, and this is a combination of the LDDMM trajectory cost, of the original metric cost of LDDMM plus the log det. They simplify together to that term. So I have, sometimes I just think of the LDDMM distance, and sometimes it's easier to think of that compound distance that also includes the integral of the divergence along the path. I don't know if that answers your question really. Not quite, I'm afraid, but I'm sorry.
Maybe I can just say a word which could explain. The distances that LDDMM is computing is on the diffeomorphism group. And here we're talking about point sets. Or if you think about images, the diffeomorphism is creating a distance on the orbit of one image. So here it would be on the orbit of the object that you're deforming, which is here a mixture of Gaussians. Now, if you got a different mixture of Gaussians, it's on a different orbit. You usually can't reach it. So you need to have something which is inexact matching with an extra distance in the ambient space or in the space where you're deforming things. And here the difference is that you've got point sets on one side, and it's a kind of asymmetric setup where you're deforming the mixture of Gaussians to fit point sets. So this is actually where is the mixture between the two. You're still having the distance, but just on the orbit of the model. But then, if you want to reach point sets, you need something else.
Okay, I could have said better. Thank you. I just want to show, if I have like 10 seconds, this is what happens like in the group-wise example. Sorry, that's a supplementary slide. So if I don't have the log det term, here is how the convergence goes. You see, it's bad because it doesn't preserve volumes. And if I do the group-wise registration without the log det term, basically the LDMM the GMM model that's supposed to explain the data shrinks, just because once you shrink it, all the distances are closer, so you optimize your energy, but totally artificially. So that log det term that preserves volumes, well, that asks for a volume preservation, it's really important for these algorithms to work. So you need to take care of it.
Thank you. I think there was
okay. Yeah. Sorry.
Just a little question about the complexity, because diff are big, and how many points do you?
Yes. So there's a little cuisine underneath that I don't show it, but I don't use all the points as support for the LDDMM framework. I have a decimation framework. I mean, that's not in the article, but generally, I like your diffeomorphism is supported by. Normally, it should be supported by all your data points, but that's very expensive computationally. I think it has to be at least in n squared, but probably worse. I haven't asked for the exact complexity, but what I do is I just keep enough data points so that they cover the whole scene. With thanks to the bandwidth of the RKHS kernel, I just manage that every point is covered, and then I launch an LDDMM trajectories with less support points, and that kind of saves a huge amounts of time.
Yeah, and because there may be some heuristic, some tricks to get much quicker some stuff if you have, for instance, the same number of points in each
Yes.
in the starting, or 8 function or whatever order between the points.
Well, basically, yes, you have to use less support points, and you can also, when you have the same number of points, you can use variants of that algorithm that I haven't shown, which is called the RPM algorithm, where you ask for a matching between every pair of points in the red and blue sets. So you could modify this thing to do RPM instead of ICP, but okay. Yeah, I haven't done it.